So that's what we were saying about using the Weinberg theorem. If somebody gives you a governing differential equation, an equilibrium equation, you come up first with the weak form, that's G, and then you use the Weinberg theorem to come up with pi, or the potential energy. Now that's one way. The other way is that if it's really a physical problem where you say that if I stretch, this is the strain energy stored in that, that's another way. So I guess if you take a look at this picture that we were talking about, so we said that um, let's say this is the governing differential equation that you start from. If you use method of weighted residuals, you can go to the G, definition of G. Or in general, if this is the governing differential equation, you can go to G. To go from G to the potential energy functional or some sort of a variational principle, in that case, you have to use the Weinberg theorem. The other way is that if you have some energy functional, then you can find this equation of equilibrium, and this is the middle one, is the one that we actually implement on the computer. Yeah.
I guess the order of the tangent towards the zero, you said like cos pi before you said that d pi equals 3.
Oh, you mean on the homework problem? I thought I mentioned it in the right order, but let me see. Okay, so yeah, I'm giving you this differential equation. So first thing you need to do is to find out the weak form. So you can find out the weak form by going from here, using the method of weighted residuals to come up with this weak form. Then once you have this weak form, you can show that there exists a pi theta by using the Weinberg theorem. Okay, so that's something that you did in class also, trying to show whether a pi exists or not. So in this case, it will exist, and then I'm asking you to find that pi. So that's this step right here. Okay, and after you're done finding pi, then you're trying to go back. So this is the next step. So if you have a pi and you take the directional derivative in the direction of some virtual displacement, what we are doing, going from here to here, is basically minimizing our potential energy. So once you have this pi functional, you can minimize it and find out that this is the same G that you got in the first part itself. Once you have this G, you can go back. Once you have this G, you can go back and calculate the governing differential equation, which is also called the Euler equation, corresponding to this. Now this step to this step was the reverse integration by parts to unbalance the derivatives. Okay? Does that sort of make sense? Okay. All right, so these are basically some of the general principles that we'll be using for this two-dimensional and three-dimensional problems also. But this procedure is pretty much what we are after. So if somebody gives us a differential equation, we do our method of weighted residuals, we come up with a principle of virtual work. And this is the principle of virtual work, which we then discretize using our finite elements. And that it is this that we implement in the computer. On the other hand, if you have some energy functional, you can minimize that energy functional and find the same sort of differential equation, same sort of virtual work principle, and again you implement that in the computer. All right, so we've developed all this machinery for one-dimensional problems. Now we're going to try to apply it to higher two-dimensional, three-dimensional problems. But even now, all we are concerned about are what are called continuum problems. So these are all continuum problems that we are dealing till now with. In general, actually after this chapter, we'll talk about beams and frames. So beams and frames and plates and all those are structural theories. This is a continuum in the sense that if you go along X, Y, Z, you're spanning a continuum material. But structural theories are special, in which what we do is we assume that our displacement is going to be of a certain form. We know that in beam theory we say that plane sections remain plane and all that, right? So those are the kinds of assumptions that we make in structural theories. This is all continuum mechanics. All right, so going back to the original problem that we were trying to solve, we said that we wanted to find a map. Basically, if we are given the structure and the loading and all that boundary conditions, then it is this map that we want to find. Given this original structure, where does it finally go to? And we said that in order to solve for this map, the governing differential equation at each and every point in the deformed configuration is this: div of sigma plus b is equal to 0, a vector. So this is a vector equation. It has 3 components, and we took a look at all those 3 components. So here, this is again just to familiarize you again with the initial notation. Whenever you see a term which has a repeated index, here j is repeated. So that should immediately tell you that we are summing over j for j is equal to 1, j is equal to 2, j is equal to 3. Okay? And the only free index here is I. So essentially what that means is that this one equation embodies 3 equations. So this really is a vector equation which has 3 equations built into it. And it is this equation that we are going to be solving in the deformed configuration. So this is a little bit of a notation here. I'm calling my original structure with this omega, and after it deforms, it will go to a new configuration which I'm calling omega subscript phi, because it is deformed through the map phi. Okay, and what I'm trying to say here is that this equation holds at each and every point in the deformed configuration. So consider something like a real structure. You go to any point in that bridge, any point, this point, in the cable, in anything, anywhere. This is the equation that needs to hold, because this is just an equilibrium equation. Okay. So let me ask you this. Do you think this picture, is it the undeformed configuration or the deformed configuration? The deformed is the final configuration, right? We cannot even build something in the undeformed configuration. So plus, actually, this is the deformed configuration at this instant, which means that obviously there's traffic, there's cars going by on this bridge. At this instant, this is the deformed configuration. So in general, obviously, you will have a dynamic term sitting in here, which says rho u double dot, right? So the actual full analysis problem is that given a time varying load, tell me how the structure responds, okay, in certain time interval. And this is the forward problem, meaning that if somebody gives you the structure, try to find where, what is the time-dependent deformation of this structure. But normally what structural engineers do is the reverse problem, design problem. So that design problem would be that tell me the structure that I should build that can carry this load. Right? That's the inverse problem. So, so you can imagine those kinds of, in fact, structural analysis and structural design are some of the hardest problems that we have. Mechanics is not that hard, actually. But anyway. So anyway, so yeah, some of the additional information that you would need to solve this forward problem, we'll stick to the forward problem of mechanics. Is that we need to, we will define some quantities given our map. We'll define the displacement as the difference between the deformed and the original configuration. And we will come up with 2 types of strain measures. This is something that we went over in the review. So if we assume that your deformed configuration is the same as your, or is approximately the same as your original configuration, then you've pretty much masked all the details of large deformation mechanics. And in that case, if you use this small strain measure, then you would still be solving the same equation, diff sigma plus b, on the original configuration, because you are saying that the deformed configuration is the same as the original configuration. On the other hand, we saw that in finite strain, when you have finite deformations, um, we defined a quantity called f, the deformation gradient. And in terms of the deformation gradient, we calculated this green Lagrange strain. This is the full nonlinear strain. And you can see that this is the part which is linear, and this is the quadratic term that's sitting in there. Okay. In addition to this kinematics, that is the description of the motion, we will also need some material properties. So we need to be able to find out if somebody gives us a structure, we need to know what are the materials that they use at each and every point. So in general, what we are saying is that we want to be able to build a relationship between stress and strain. So if it is small strain, this is the type of relationship that we said we were going to use. And again, this C double tilde is actually a fourth order tensor. This fourth order tensor acts on a second order tensor to give you back a second order tensor. Okay, and since it is a fourth order tensor, it actually has these 4 subscripts, 4 indices. And what does that mean? If you have sigma ij, this is the sigma ij, we know that it has 9 components, 3 cross 3, right? Epsilon ij, actually there's a mistake here. So can somebody tell me what's the mistake in this? Right, it should be KL. So make that correction. And now, how many epsilon KL also has 9 components? How many components are there inCijkl? 81. And the reason is that 3 times 3, so each IJKL will have 3 indices each, right? So 3 times 3, 9, times 3, 27, times 3, 81. So those are the 81 constants, material constants, that you will have for a general elastic material like this. But we know that actually there are some symmetries in this C. So one symmetry is straight away, that is called a major symmetry, that if you calculate the strain energy stored at a point, that is half epsilon ij timesCijkl times epsilon kl. So that is actually symmetric. So ij is symmetric with kl, and that reduces our material constants from 81 to 6 times 6, 36. And then there is something called a minor symmetry. Minor symmetry is because the strain and the stress themselves are symmetric. So what that does is that it reduces our constants from 36 to 21. And then if you further make the assumptions that my material is isotropic, it is linear, and it is elastic, then one can show that the number of constants, material constants needed to define a general isotropic linear elastic material, there's only 2 constants that are required. So those 2 constants could be your Young's modulus and Poisson's ratio, or it could be this Lamé parameters, which is lambda and mu. So here, one thing I think maybe some of you didn't realize earlier was that this lambda is a scalar, and this trace of epsilon, this is also a scalar. Epsilon, this is a strain tensor. Trace of the strain tensor is actually just the sum of the diagonal entries. So that's also a scalar. So this thing is a scalar multiplied with the identity matrix. This thing is a scalar multiplied with the strain tensor. That gives you back the stress tensor. That's the Hooke's model that we also did before. And the same thing written out in indicial notation. And the reason I'm stressing indicial notation is because we are going to start to use this notation to derive our weak form. Because we don't want to write out 3 equations every time we want to do integration by parts or those kinds of things. So make sure you are comfortable with these types of indicial notation, and we'll do that derivation in class today. So this was for the small strain material model. And for the large strain, we talked a little bit about hyperelasticity. And we said that hyperelasticity is the class of materials that uh, for which we can define some strain energy density function. So this is a strain energy density function, means that if you go to any point in your structure, you can define the strain energy stored at that point in terms of the deformation. So if you deform that point with F, the strain energy stored can be given by this. If such a strain energy functional exists, then you can say that that material is hyperelastic. Okay, and so a couple of different ways of deriving the stress from the strain in these hyperelastic materials is, first way is actually you can calculate something called the first Piola-Kirchhoff stress tensor, and that is just you take this scalar function, take its derivative with respect to f, that will give you p. And the important thing to note here is that p and f, they are what are called work conjugate, right? So in small strain, we say that this small strain and stress are work conjugate. In large strain, this first Piola-Kirchhoff and f, they are work conjugate. Similarly, this is what is called the second Piola-Kirchhoff stress tensor. And this is just a definition. There's not a whole lot of physical meaning to it. Towards the end of this chapter, we'll actually show you that people didn't just come up out of thin air for these definitions. If you just follow the weak form, transform your equations, these definitions come out of that. So I'll show you that towards the end of this chapter. But this the second Piola-Kirchhoff stress tensor is actually work conjugate to E. This is the E that you had for Green-Lagrange strain. So in finite deformation, if you are working with Green-Lagrange strain, the stress measure that you should be using is the second Piola-Kirchhoff stress. And once you have either P or S, you can actually calculate Cauchy stress, which is the real stress. Real stress meaning it is the real stress in the deformed configuration by using these relationships. So note that sigma is some function of P and F, and if you pre-multiply this equation with F, then you get sigma for the second Piola-Kirchhoff stress tensor. And this J is nothing but the determinant of F. So this is just a lot of definition, but we'll keep this in mind as we go and derive our weak form for this 2D and 3D problems. Okay, so going back to small strain formulation. So we know that our stress is a tensor that we can represent with 9 components like this. And similarly, strain is a tensor that we represent with 9 components like this. But this sort of a notation is not really easy to implement on a computer. So what people did was they came up with a different notation for the stress and the strain. So this notation is called the Voigt notation, where all that we are doing is we are taking the diagonal terms. Those are the first 3 terms in this quote-unquote vector, and we are taking these 3 off-diagonal terms and expressing them here. So we have converted this 3 cross 3 9 components to 6 components. We are only working with the symmetric part. We know that these bottom 3 are actually equal to the top 3. That's why we are not extending it up to 9 cross 1. We are just limiting it to 6 cross 1. And we know that this sigma is related to epsilon with those C, I, J, K, L, right? And I just told you that in general you would have 36 constants. So just take a look at this matrix right here. This is a 6 cross 6 matrix. Obviously there's 36 constants, but if you restrict your material to linear elastic isotropic material, then you can express all the material constants in terms of 2. And in this case, I'm using the Young's modulus and Poisson's ratio. And there's again a little bit of a switch of notation just to be consistent with the books. In one-dimensional, we've been saying that Young's modulus is C. Now we'll just start saying that Young's modulus is E. So it's just a change of the variable name. Okay. Um, all right. So what we've done now is we've said that the stress is some linear function of the strain, and the strain is this strain that we are defining here. This is called the engineering strain, uh, where these off-diagonal terms, we actually have a factor of 2 sitting in there. So people who do measurements with strain gauges and all that, they actually measure the changes in angle. That's why this quantity, this is actually called gamma xy, gamma yz, gamma zx. So when we implement things in finite elements, we will also work with this. And another reason for using this factor of 2 is actually that it makes this stiffness matrix or this material elasticity matrix a symmetric matrix. So in general, you can also think, another way of thinking about this factor of 2 is that if you had started out with a 9 cross 1, then this matrix would be a 9 cross 9 matrix. This vector would be a 9 cross 1 without the factor of 2, and all that you've done is folded the 3 equations up onto this part. That's why this gets doubled, and you lose the 3 equations for this stress, and ultimately you end up with a symmetric matrix. So anyway, this is just a different sort of a notation, and all we are saying is that this stress vector is a function using the D elasticity matrix of the strain vector. Now, this is very bad notation if you try to go by the go by the rules of mechanics, because we know that stress has to be a tensor, strain has to be a tensor, but just so that we can implement it on a computer, we are calling this that we represent this stress tensor in a vectorial form. So this is only a computer implementation sort of an equation. That's why I'm saying that you need to be careful about this definition. Okay. All right. So this is what we would have in a general 3-dimensional case. If we restrict our problem to 2 dimensions, there are 2 types of problems that we normally have. One is called a plane strain and a plane stress and a plane strain problems. And I'm sure most of you have already seen these things before. But in the first problem, the plane stress problem, we say that sigma 33 is 0. And that actually is a good approximation for problems where you have thin sheets. Okay. So for example, this is a thin sheet, or even if you have something like a shear wall, which is thin, you can say that the stress in the vertical direction is going to be 0 because this is a thin sheet. If you stretch it, then it will just become thinner, and the stress in this direction will be very small compared to the stress in the in-plane directions. So this would be a good approximation to make for thin structures. And all the other components of stress that have 3 in them, they are all 0. Okay. So once you take these relationships and plug them back into this big 3-dimensional matrix, what you will see is that you can eliminate a lot of terms, and you come up with this new stress-strain relationship for 2-dimensional problems, for 2-dimensional plane stress problems. So the stress is just going to be sigma xx, sigma yy, sigma xy. Sigma yx is just symmetric part of this. And that can be expressed in the same way that we had before in terms of the strains in that plane, in the xy plane. And this is also the similar type of a notation where I'm just using the subscript plane stress for the elasticity matrix. Now, one thing to keep in mind is that the strain in the third direction is not 0. So obviously, if you stretch a thin plate, it will try to collapse in the third direction. So the strain in the third direction is not 0, but the stress is. So the strain in the third direction can be actually calculated just by plugging it back into the full three-dimensional equation. So is there any question or doubt about plane stress? Okay. Similarly, we have this plane strain equation. Now, in plane strain, what we say is that our strain in the third z direction is supposed to be 0. So this kind of an approximation holds true for structures which are very long, something like a dam, and this is a water pressure distribution on the dam. If you consider one plane of cross section of this dam, that you can express, you can say that there is that this plane is not going to move at all in the third dimension. That's why you are able to say that all the strains in the third direction are going to be 0. But that also means that there is, since we have constrained the strains in the third direction, there is going to be stress in the third direction. Okay. So if you plug this into your full three-dimensional equation, what you get is a different elasticity matrix. So you have these are the same stress components in plane, strain components, and this is the elasticity matrix for the plane strain case. The only difference is some of the components are different here. So these are the two types of restrictions in 2 dimensions that people try to solve. All right. Let's see. All right. So what we'll do now is try to start with the strong form of our equations, and we will use our machinery that we developed for the one-dimensional problem to come up with the equation that said, KD is equal to F. So we'll use the same machinery for these problems, and try to see how to apply that machinery for these 2 dimensions and 3-dimensional cases. So I'm calling these strong forms because this is the governing differential equation along with the boundary condition that we were trying to solve. But note that in this case, the solution U, the displacement at any point, is going to be a vector field, which means that if you go to any point x, there's going to be a small x displacement, small y displacement, small z displacement. So essentially this problem, we are trying to solve a vector field over the entire domain of our problem. So let's try to restrict first, try to understand how this machinery works for a scalar field problem, and then we'll go back to this elasticity vector field problem. So this problem, which is also given in your books, and maybe I should have mentioned this, so you can use the references for this part of the chapter. So from the Reddy's book, you have chapter 8, 9, and 11. This is all for the entire chapter 2. This is not just for today. So and from the Hughes book, you have chapter 2, and from the Zinkewicz and Taylor, you have chapters 2 and 3. So in Reddy's book, we've covered until chapter 4. Chapter 5, 6, and all those, they are about beam theory and some eigenvalue problems. So we'll come back to beam theory later, but chapter 8 and 9, they are about these 2-dimensional problems. Okay. All right. So let's take a look at a scalar field problem. This problem is of a heat conduction. So what we're saying is that So what we're saying is that this problem, we have some domain, some structure, or some material, and we have constrained one portion of the boundary of that material, which we are calling gamma d, which is similar to our displacement boundary condition, but we have constrained it in such a way that we know that we are applying some temperature at that point. So this is very similar to your homework problem also. I'm saying that on this edge of the structure, my temperature is some, let's say 100 degrees centigrade. On the other edge of the of this structure, I'm applying a different temperature profile. So I have applied high temperature here, low temperature here, and I want to see what is the temperature profile within the structure. In addition to that, there are two free edges of the of this structure. So these two free edges are like our force boundary conditions, or on the portion of the boundary where we apply tractions or forces. But instead of forces in this heat conduction problem, this is a heat source. So we are sending in some amount of heat through this edge of the of this material, and this is simply exposed to air. So we are saying that there is no heat exchange. There could be heat exchange, but we are trying to find that as part of the problem. So so the governing differential equation in this case is very similar to what we have before. This Q is a quantity which is called pointwise heat flux. This is something very similar to stress. And F is a pointwise heat generation. This is something very similar to the body force. So if you have a heat source at any point in your structure, that is going to be denoted by F. That's the body force term. This term is related to the gradient of the temperature. So let me show you. Yeah, right here. The gradient of the temperature is theta is the temperature at any point in the problem, and gradient is just going to be a vector. Since theta is a scalar, its gradient is going to be a vector. And in our structural problem, what we had was this theta was the three displacements. So if you take the gradient of displacements, you would get a tensor. But in this case, if you take the gradient of a scalar, you get a vector. Okay, and I'm denoting this vector with a 2×1 matrix, but this notation is actually valid for the equal to. So this is again using the same initial notation. I'm saying that the gradient can be represented with d theta over dxj, and since this index j is repeated, I know that I need to repeat it for I is equal to 1 and 2. This is a two-dimensional problem, that's why we are saying that j needs to be repeated for 1 and 2. If it's a three-dimensional problem, then j would be repeated for 1, 2, and 3. Okay. So similarly, this temperature gradient is something like our strain in the structural problem. Okay, and we know that our strain is related to stress in the structural problem. So here, the temperature gradient is related to Q, the heat flux, by the material conductivity, which just measures how fast can heat transfer through the material. So that relationship is given by this. You take your temperature gradient, and heat conductivity in general is going to be a tensor. In 2 dimensions it's 2×2, and 3 dimensions it's 3×3. And this is the relationship that that is similar to our Hooke's law for our structures. So we are saying that heat flux is some tensor times our temperature gradient, which is similar to stress is the C double tilde matrix times strain tensor. So this is very similar problem. The couple of good things about this problem is that the size of the domain, it doesn't deform. And second is that we are trying to find a scalar field instead of a vector field. So if you substitute this back into the governing differential equation, you get this and this equation. And this again is a very similar equation to what we had in structures. Couple of different ways of expressing the same equation, and try to let me know if you have any question on this initial notation right now, because we are going to use this for our derivation. So divergence of this quantity that's just going to be written out as d over dxi. This quantity in here is this kij times applied to the temperature gradient plus f is equal to 0. So how many equations are here in this equation? Why is there two equations? I is actually not a free index here, right? Right, so I is not a free index. I is repeated here, j is repeated here. So this is just one scalar equation. So this is a scalar field problem, so we will have just one equation. As opposed to this, the structural problem, there were three equations in there. But this is just one scalar equation. And another way of writing this equation is using this shorthand notation for the derivative in initial notation. So did you guys see this? Have you seen this before? So normally what we do is when we try to take derivatives, we don't want to write out this entire thing d by dxi. So what we do is we replace this with a comma I, and this is a common initial notation. Again, this is just notation, so there's nothing very fancy or new about this conceptually. So what we're saying is that d theta dxj is theta comma j, and kij is acting on this. So another way of interpreting this is that kij is a 3 cross 3 or 2 cross 2 matrix, right? And the column is going to act on the row. So if you were to write this out, you would have a 2 cross 2 matrix acting on a 2 cross 1 vector, which is this bracketed part. And then you take this whole quantity and you take its derivative with respect to I. And wherever you have a double index, you are going to sum up these types of quantities for I is equal to 1 and 2, j is equal to 1 and 2. So you have to consider all possible combinations of this. So how many total terms are going to be there in this? Two terms for I and two terms for j. So that would be 2 times 2, 4. In general, if it is 3-dimensional, it would be 9 terms. Okay. So yeah, I've written it out in the matrix form here as well. So what we're going to do now is going to take this equation and we are going to start writing our method of weighted residuals and try to see if we can convert this into the form kd is equal to f. Okay. So so just like in the one-dimensional part, yeah.
How do you set the prism to one equation before there's four terms in it?
Right. So yeah, there's going to be, this is, if you take this matrix, apply it on that, you will get a 2 cross 1 vector, right? And this 2 cross 1 vector multiplied with that is a scalar back. So it is a scalar equation. Okay. Any other question? Okay. So now what we're going to do is we're going to take the same machinery that we had for the one-dimensional problem and apply it to this case. So we're going to say that divergence of k grad theta plus f, this was our scalar governing differential equation. We will take this equation, multiply it with some virtual theta bar, right? And we are going to integrate this over our domain. So our domain is, right now we have just chosen a two-dimensional domain, x and y. So we are going to integrate it over a domain which I'm going to call omega and d omega. So, and then I'm just going to say that this is my quantity g theta comma theta bar. This is how we start all types of method, all types of problems. Take the governing differential equation, no need to add any boundary terms. Let them come out naturally from your integration by parts. Okay. All right. So now what we're going to do is let me write this in a little bit different notation. But before that, maybe I also need to point out that this integral something over omega in 2 dimensions, it is actually a double integral. In 3 dimensions, it is going to be a triple integral. So for a very simple case, like if you have a rectangular domain in 2 dimensions, let's say that would be something like this. So let's say this is your rectangular domain in 2 dimensions, and the limits along the x-axis are a and b. The limits along the y-axis are c and d. Then this double integral can simply be written as the same quantity dx going from a to b. You take whatever you get from there, you apply dy and integrate that from c to d. So this kind of you can set those types of limits only if your domain is a rectangular or square domain. If it is a general type of domain, you actually have to parameterize that, and you have to use a special double integration. You have to be careful about that. So anyway, now we're going to write this in using indicial notation. So theta bar is a scalar, no need for any indices. Div, this term right here, what we had was kappa ij applied on theta comma j, and derivative with respect to I plus f d sigma. So is this first term exactly equal to this? This is just writing it in a different notation without the indices, and this is the same thing written with the indices. They are both one scalar equation, so this is perfectly fine. In 3 dimensions, it is not so, so we will have to actually add a unit vector to that. But let's restrict to this. So now we are going to try to balance the derivatives. You can see that the derivative on theta, the real temperature or the real displacement, quote unquote, there is a double derivative on that. Derivative with respect to xj, derivative with respect to xi. And to balance the derivative between the real temperature and the virtual temperature, we will use integration by parts or something analogous to that. So we want to balance these two. And in order to do that, what we are going to do is we are going to apply the product rule. So that is basically what integration by parts is in 1 dimensions. So consider this. If I have theta bar kappa ij theta comma j, actually let me replace this thing with this part right here. This is qi. Is that right? So kappa ij, this bracketed term in there, that is qi. That's the heat flux vector. So what we are going to do now is we are going to say that consider theta bar times qi whole derivative with respect to I. So now this is nothing but divergence of this whole quantity. So if you were to write it without the indices, that would be divergence of theta bar times q vector. So the quantity inside the parenthesis is a vector because it's a scalar times a vector. And if you apply the product rule to this, what you will get is theta bar comma I times qi plus theta bar times qi comma I. Right? So this term right here, qi comma I, is right here, qi comma I. So what we'll do is we'll take this term to the left hand side, transfer this term over to the right hand side, and we are just basically deriving the method of or integration by parts for 2 dimensions and 3 dimensions that we know for 1 dimension. So without the indices, what this looks like is gradient of theta bar times dotted with q plus theta bar times div of q. So this means that I can express theta bar times q I comma I is equal to theta bar qi whole derivative minus theta bar comma I qi. All I've done here is I've taken this term to the other side, so that becomes a minus sign, and just flip the order of left hand side and right hand side. So I will take this thing and substitute it in my weak form. If I do that, what I get is g of theta comma theta bar is equal to minus integral theta comma I times kappa ij. Now I'm substituting back for qi, so theta comma j, and d omega. This is integral over the domain plus this boundary term. So this is what leads to the boundary term in our one-dimensional case. So let me write that out here. Theta bar q I comma I d omega. Right now it is not a boundary term, but I'll show you what how this becomes the boundary term. And then finally you have the forcing term, which is just integral theta bar f d omega omega. All right, so in one dimension, if you remember, when we say that integral du v is equal to u dv plus v du, that integral we can say is equal to u v. This is the boundary term over 0 to L, and this is equal to basically these two quantities on the right hand side. But in 2 and 3 dimensions, what we use is called the divergence theorem. So the divergence theorem is something like this. If we have a vector, if we try to integrate the divergence of a vector over a domain, divergence of v d omega is actually equal to integral over the boundary of that domain. So let me denote that boundary by gamma with v dotted with n over d gamma. So essentially what we are doing is the same thing that we do in one dimensions. This equation, we call it the divergence theorem, but this is something very simple. In one dimension, what this looks like is integral d, let's say f dx a to b. What is the answer to this? If I have some function f, I take the derivative of that and I integrate it back again. So the answer to that would be f itself, right? I take the derivative, I integrate it back again. What I would get on the right hand side is f, and the limits are a to b. So what we are doing is fb minus fa, and this is all that we are trying to do here in 2 dimensions also. So this equation, or this relationship, says the exact same thing. If you have a domain omega you transform the derivative divergence to a v dot with n, where n is the normal vector to that domain. So this is the same relationship in one dimension. This is the same relationship which is called divergence theorem in 2 and 3 dimensions. So anyway, I guess we'll continue with this next time. So let me know if you have any questions about the homework on the forum or anything. Okay. All right. See you Friday.